Hello and welcome. Today, we are diving into the fascinating world of lenses. Have you ever wondered how glasses or cameras bring blurry objects into focus? Well, that's all thanks to lenses. Let's start with the basics. Lenses are optical devices designed to bend light. This bending allows lenses to form clear images of objects that might otherwise be blurry. Now, there are two primary types of lenses: concave and convex lenses. Convex lenses are often referred to as converging lenses. They have the ability to bring light rays together to a single point. Think of a magnifying glass. It uses a convex lens to focus light onto a small area to create an intense spot of heat. On the other hand, concave lenses are diverging lenses. These lenses spread light rays apart, making objects appear smaller. You'll often see these used in optical devices like telescopes and eyeglasses for people with nearsightedness. So, what's the magic happening here? Lenses work by bending light at the interface between air and glass. This bending changes the direction of light, enabling us to see things more clearly, whether we are reading a book, taking a picture, or examining distant stars. Quick insight: lenses are not just part of everyday objects like glasses, they're also integral in scientific tools like microscopes and telescopes. They help us see things up close and far away, shaping the way we interact with the world around us. Let's dive deeper into how light interacts with a convex lens. In a convex lens, when parallel rays of light pass through, something fascinating happens. They don't just keep going in straight lines. Instead, they converge or come together after passing through the lens. This is the key characteristic of a convex lens: its ability to bend light and focus it at a point. As you can see in the diagram, the rays all focus on a single point after passing through the lens. That point is called the focal point, which we'll discuss in the next scene. But what's important here is understanding that this converging behavior allows convex lenses to focus light, which is why they are used in so many devices, from magnifying glasses to cameras and even eyeglasses. The focal length, the distance between the center of the lens and the focal point, tells us how strongly the lens bends the light. The shorter the focal length, the stronger the convergence. This is what allows convex lenses to magnify and focus images, making them incredibly useful in various optical applications. Have you ever used a magnifying glass to see something more clearly or look through a microscope at tiny cells? What's happening behind the scenes? It's all about how lenses bend light to magnify objects. Let's dive into the physics of it. To understand how a lens forms an image, we use a very important formula called the lens equation. This equation is written as 1 divided by f equals 1 divided by v minus 1 divided by u, where f is the focal length of the lens, v is the image distance, and u is the object distance. This equation helps us figure out where the image will appear when light passes through a lens. Next, let's talk about magnification. Magnification tells us how much larger or smaller the image is compared to the object. We calculate it with the formula m equals v divided by u, where v is the image distance and u is the object distance. This ratio helps us determine whether the image is magnified or reduced. If the value of m is greater than 1, the image is magnified. Magnification is not just about numbers, it also relates to the size of the image compared to the object. For example, think of using a magnifying glass. When you look at a tiny ant, the image appears much bigger than the actual ant. That's magnification in action. Lenses bend light in such a way that the image we see is a clearer, magnified version of the object. The lens formula helps us determine the position of the image formed by the lens. This is crucial in everything from photography to designing optical instruments like cameras, eyeglasses, and telescopes. With this formula, we can predict how the image will be focused and how much magnification will occur. In a nutshell, whether it's magnifying a small object or focusing light to form a clear image, lenses are at the heart of many everyday devices. And by understanding the lens formula, we gain insight into exactly how they work. I hope this helps you get a clearer picture of how lenses help us see the world in a new light. Catch you in the next session with another fascinating concept of physics. Welcome, everyone. Let's dive into the fascinating world of image formation through lenses. Imagine you're holding a magnifying glass. Ever wondered how it can make small objects look bigger? Well, that's all about how lenses form images. There are two main types of images we'll talk about: real and virtual images. Real images are formed when light rays actually converge at a point. This is like when the sunlight passes through a magnifying glass and focuses to burn a piece of paper. The image can be captured on a screen, which is a real-world demonstration. Virtual images, on the other hand, occur when light rays seem to diverge from a point. You see these in things like mirrors. You can't project a virtual image onto a screen because, well, the light rays don't actually meet, they just appear to come from a point behind the mirror. Convex lenses are fascinating because they can form both real and virtual images depending on the object's distance. If the object is far from the lens, you'll get a real image. But if it's close enough, you'll get a virtual one. Quick insight: real images can be projected onto a screen, but virtual images cannot. Think of it this way: you can't put a shadow on a screen if the light rays aren't actually hitting it. And that's how lenses give us the ability to both magnify and create projections. Pretty cool, right? Hello, everyone. Let's explore how magnifying glasses work, and trust me, you've probably used one before. It's fascinating how a simple lens can bring tiny details into sharper focus. So, what happens inside a magnifying glass? It uses a convex lens to form a virtual image of the object you're looking at. Let's break it down. When an object is placed within the focal length of the lens, something cool happens. The image that forms is not only virtual, meaning you can't touch it, but also upright and magnified. It's like looking at something through a telescope or your favorite magnifying glass. Everything becomes clearer and bigger, right? Now, think about your magnifying glasses. These are a perfect example of this principle. They help us zoom in on things that are too small to see clearly, like reading the fine print or examining an insect closely. To wrap up, a convex lens, when used properly within the focal length, creates a virtual, magnified image that makes small objects much easier to view. It's all about bringing distant details into sharp focus. Welcome to this lesson on solving lens problems. Have you ever wondered how we can see objects that are far away or very close? This is all thanks to lenses like the ones in glasses or cameras. Let's dive in and see how lenses work with a simple formula. In this example, we are using a convex lens with a focal length of 20 centimeters. The object is placed 30 centimeters away from the lens. Now, we need to find the image distance, or how far away the image is formed from the lens. The formula we use for lenses is 1 divided by f equals 1 divided by v minus 1 divided by u, where f is the focal length of the lens, v is the image distance, and u is the object distance. Now, let's substitute the values we have into the formula. We know that the focal length f is 20 centimeters and the object distance u is negative 30 centimeters because the object is placed in front of the lens. So we substitute 1 divided by 20 equals 1 divided by v minus 1 divided by negative 30. Notice the negative sign for the object distance. To solve for v, we first simplify the equation. 1 divided by 20 equals 1 divided by v plus 1 divided by 30. Now, let's solve this for v. We rewrite this as 1 divided by v equals 1 divided by 20 plus 1 divided by 30. Finding the common denominator, which is 60, we get 1 divided by v equals 3 divided by 60 plus 2 divided by 60. So, 1 divided by v equals 5 divided by 60. Now, flip the equation to find v, and we get v equals 60 centimeters. So, the image is formed 60 centimeters on the opposite side of the object. This is a great example of how lenses can form real, inverted images. Keep practicing, and you'll get the hang of it. See you next time for more exciting physics. Welcome to a quick overview of lens properties. Imagine you're looking through a magnifying glass focusing on a tiny insect. What happens? The image becomes larger, right? This is the power of lenses at work. Lenses can bend light in such a way that they form real or virtual images, and this depends on the object's distance from the lens. Now, there's a simple formula that governs the behavior of lenses. It relates the focal length, the object distance, and the image distance. This relationship allows us to understand and predict the nature of images formed by the lens. Next up, let's talk about convex lenses. These lenses are fascinating because they help us magnify objects. You can find them in magnifying glasses, eyeglasses, even in microscopes and cameras. They help us see things in more detail than the naked eye can. To wrap it up, think about how we use lenses in our daily lives, whether it's reading a book, adjusting your glasses, or using a telescope. These simple tools are powerful in transforming how we interact with the world around us. So, that's the essence of lenses bending light to form images. Next time you pick up a magnifying glass or adjust your glasses, you'll know the science behind it.